rise to so many equations which we could see, but main equation was that energy of incident photon was equal to kinetic energy, the maximum value of kinetic energy, as well as the work function. This was the total formula, or total, you can say the definition of it as well as the formula of it. So this much we had seen. De Broglie waves was left. Let us start with de Broglie waves. No, this graph was also left. Yes, class. See, this equation which we have. This equation that we have, EV naught, this is equal to the kinetic energy. This is kinetic energy is equal to h nu, that is the frequency, minus the work function that is present. Now see, if we divide this equation by this E, so what will happen? Here E, here E, here we'll have E. So the equation will look like this. Potential, stopping potential, that is V naught is equal to H by E over here, nu, minus phi naught by E. Now look, is it similar to this? Y is equal to mx plus c, where where m is the slope of the graph, c is the y-intercept of the graph. So c, that is the y-intercept of the graph, this is equal to minus phi naught by E. So minus phi naught by E, see, this is the negative y-intercept. Y-intercept, I hope you understand, if this is the y-axis, any part that cuts it, intercept is known as this, from the origin when we cut it. So if this is the origin, then this is known as the y-intercept. So y-intercept can be positive, negative. Here you can see from this equation, this is minus phi naught by E. So if it is minus phi naught by E, that means negative y-intercept. Like this, you have the graph. And if you want to take out the slope of this, slope means tan theta only. Tan theta, if you calculate, that will be directly equal to C, H by E, because this is the slope of the graph. So this graph can come, and this representation can be asked to you to show this graph and write all these points, like what is the slope, what is the y-intercept. Fine, or it can give you a numerical form also. This value will be given in the graph. We'll do questions on this also later on, we'll see. First, let us complete the chapter. Note down this part, class. Then we'll start with de Broglie waves. Done, class? Okay, class. Now coming to de Broglie waves. So, see, class, from your de Broglie waves part, no, there is one experiment, Davison and Germer's experiment, that has been deleted from your syllabus. All right, this year it is deleted. Till last year it came. So this year it is deleted. So de Broglie wavelengths is now a very, very short topic for you because that part has already been deleted. So, see, there was a scientist, French physicist was there. His name was Louis Victor de Broglie, something his name was. At the end, de Broglie was the name. So, do you pronounce it actually as de Broglie? Mean the actual pronunciation is de Broglie. But just for the convenience, no, because otherwise spelling errors will occur, and the theory part also comes from this. That's why we all usually pronounce it like de Broglie. So he gave the hypothesis. He put forward a very bold hypothesis was provided by him. He said that continuously we have been studying photoelectric effect of this particle, photoelectric effect of this electron. Like this, we have been studying, right? He put forward that material particles that are in motion, they also display wave-like properties. So the waves associated with these material particles, these are known as matter waves or de Broglie waves. This means what? You can imagine an electron is there. Electron is a particle, so it will have all the properties that a particle possess, right? But when the electron will exhibit wave-like characteristics, the wave-like motion, that wave that will be produced will be known as de Broglie waves or matter waves also. You can call it as matter waves as well. So he used certain criteria, he used certain experiments. One was, you must have heard of Einstein's mass energy relationship. Are you aware of that? Theory of relativity, which he gave, and the mass energy relationship, which govern all the forms of the physical universe. E is equal to mc squared. This is a very famous equation. So he used this equation, fine. use this equation. And another point he also mentioned that electrons, protons, neutrons, they do not just behave like mass points, but they also exhibit the wave nature in motion. So one equation was this. Another equation that he used was the equation that we have been studying, h nu. Right. So both the energies are actually same. Both the energies are associated with the electron. So equate both of these. mc square is equal to h nu, or write down h c by lambda. See, this c gets cancelled. Lambda becomes h by mc. This is the formula for it. This is specifically for speed of light. So de Broglie's wavelength can be written as h by mv also. Velocity for any other light as well. Not just necessarily be applicable for speed of light. It can be applicable for any medium. And mass into velocity. Can anyone name this term, mass into velocity? Mass into velocity. Yes, class. Can anybody remember this?
Momentum.
Momentum. Yes, correct. Good. Momentum. So h by p, where p is the momentum. This becomes the formula for this de Broglie waves equation. This is known as the de Broglie's wave equation. And there are 4 findings that he could drop from this. First finding was that, see, lambda and the wavelength relation with momentum is inversely proportional. Wavelength is inversely proportional to momentum. So first hypothesis that he gave, or the conclusions that he gave, characteristics for the wave-like particles, was the first fact was this. Second fact was, see class, if velocity is 0, if we say velocity is 0, so lambda becomes infinity. So this shows what? That waves are associated when particles are only in motion. Right? As soon as the velocity is 0, that is the particles come at rest, wavelength immediately becomes infinite. But as soon as the velocity is there, it means the particle is in motion. Then only de Broglie wavelength exists. This is the conclusion. Because when velocity is 0, de Broglie's wavelength was infinite, which had no meaning, no significant meaning. But as soon as velocity will be there above 0, it will be. That is, it will not be at rest. So certain amount of de Broglie wavelength will also exist. Right. So these were the 2 conclusions that were drawn. Then the third point that was given by the hypothesis of all these, it was that these are also known as matter waves first, because the particle need not necessarily have a charge. Right? They do not necessarily have a charge with them. So that's why they are known as matter waves as well. These are known as matter waves as well, because they do not necessarily have a particular charge on them. And the last part that is here present from me is that electromagnetic waves we have studied. No, the entire lesson we have seen. So many waves like X-rays, gamma rays, infrared rays, UV rays, so many rays were under the electromagnetic spectrum. And all these rays exhibited the same conditions, same phenomena, same formula, all these things were similar for all the electromagnetic spectrum, like traveling with the speed of light. It was fixed for all of the EM waves. So certain things were fixed, like electric field, magnetic field will be perpendicular to each other, and also to direction of propagation. So for any wave, be it X-ray, be it microwave, it will be there, this point that I have just mentioned. So in case of de Broglie wave, then these are not EM waves. It means all these things, whichever you have, whatever properties you have studied for EM waves, that will not be valid for this. So EM waves, I'll write down, they are not EM waves. Not EM waves. Because first thing is that they are associated with accelerated charge particles. So that differs with all the criteria from electromagnetic wave. So this is the basic thing. H is equal to mv is there. This is important. H is by p. All these points are important. One more formula you can say, see, kinetic energy is p square by 2m. From here, momentum can be written as 2m into kinetic energy under root. So lambda can be written as h by under root 2m kinetic energy. But see, now any modification you can make. If you know all the modifications, all the formulas for momentum, anyway you can relate momentum with whatever is given in the question. So this is used a lot, and in many schools this question have come in their exams. So de Broglie's wavelength, all the modifications are important. Rest of the modifications were from the Davison's and German experiments, so that will not now be included in your syllabus. All right, I hope this is clear. Note down all these points. Okay, class. Now some questions are there from de Broglie wavelength, as well as certain practicing questions are also there that we'll see at the end. Because another important lesson that you have is atoms from your modern physics. So this is also not a very big lesson. See, in atoms, the first thing that comes is in relation with what we have studied. That is de Broglie wavelength only. So, first thing that comes in this lesson we'll start with is Bohr's atomic model only. Bohr's quantization condition is there. Bohr's quantization condition. Now, see, according to de Broglie hypothesis, electron has wave character also. That was what we have studied. Just now we had seen. So, circular orbit can be taken to be stationary energy state only if it contains integral number of de Broglie wavelengths. It means, see, these are the orbits of electron. This is the path that electron covers when it is revolving around the nucleus. If in the center you have the nucleus. But apart from this, it exhibits the wave-like path also. It traverses in wave-like path also. So the combination of both of these, the discrete standing waves characters that also come, as well as the proper particle nature that is observed when the electrons revolve. This is Bohr's quantization condition, as in, let me expand you. This says that the circumference that electron covers, this circumference that electron will be covering will be 2 pi r. Let's say radius is r, 2 pi r. Fine, this radius is 2 pi r. And what did Bohr said? What did de Broglie said? That particles have wave-like character as well. So it means this 2 pi r for this circle, this is equal to what? This is actually equal to the waves, de Broglie wavelength. No, because this wavelength has been exhibited by the electrons which possess wave-like characters. So this is equal to lambda. Now, how many lambdas? 1 wavelength only, 2 wavelength only, 3 wavelength, 4 wavelength, any specific value of wavelength, one such value. So that we take it as n lambda, any integral multiple, any integral number we have taken. That can be 1, 2, 3, starting from 1 to 3, any value we can have. So this condition, this is Bohr's quantization. This is actually not, this is just Bohr's quantization condition. But if it is Bohr's quantization condition for angular momentum, let me tell you this. Bohr's quantization for angular momentum. So see, now relate with this formula. Lambda was h by mv. We did de Broglie wavelength. Lambda was equal to h by mv. So 2 pi r lambda can be, this is 2 pi r. Now put the value of lambda in this equation. Put the value of lambda here. So this becomes 2 pi r equal to nh by mv. Correct? 2 pi r is equal to nh by mv. Just bring this mv here, shift the 2 pi over here. Just exchange these two quantities. If you exchange these two quantities, one in the numerator, other in the denominator, this will be mvr is equal to nh by 2 pi. Can anybody tell me what is mvr? MVR.
Centripetal force.
No, that is mv square by r. This is angular momentum. The way if linear momentum was mv. So if you multiply linear momentum with r, that gives you angular momentum. The way you have r cross f gives you torque. Similarly, here you have the linear quantity multiplied by radius vector the new quantity. Linear quantity multiplied by radius vector, new quantity, that is angular momentum. So angular momentum, which is mvr, this is equal to nh by 2 pi. Now this is known as the famous Bohr's quantization condition for angular momentum. So only those circular orbits can be allowed to be stationary states when electron has integral multiple of this term h by 2 pi. This is known as the quantization condition of Bohr's. Fine. Bohr's quantization condition for angular momentum is asked. So specifically, you have to mention angular momentum. If angular momentum term is not mentioned, then normal simple condition, that is Bohr's quantization condition, is 2 pi r is equal to n lambda. But usually in maximum questions, you have to show and share it till this step only. Till this step. Fine. So L is equal to MVR, which is equal to NH by 2 pi, and N is any number starting from 1, 2, 3, 4, up till all the numbers. All right. Now he gave certain postulates as well. 4 postulates were major postulates were given by Bohr. Then I'll give you time to note it down and you can clarify if you have any queries. Just understand the postulates. Postulates of Bohr's theory. Now, see, the first postulate that he gave was based on the nuclear concept. So, nuclear concept, he simply said that atom consists of, there is a small and massive central core. Small, massive central core, and this is known as the nucleus. This is known as the nucleus. Right? Now, this was said by him. He said that centripetal force that is required for the rotation, this is provided by the electrostatic attraction between the electron and the nucleus. This, when we were doing electrostatics, that time only we had discussed this, that between electron and the nucleus, electrostatic force of attraction is present. This is the electric field that is present, which provides the necessary centripetal force for the rotation or revolution of electron around the nucleus to be possible. So electrons revolve in orbits. There's a small, massive central core, which is known as nucleus. And the electrostatic and electrons are attracted by the nucleus through electrostatic attraction. This is the first condition, first postulate that was described by him. Everything in detail, I'll share it right now only after few minutes. I'll share the notes, the handwritten notes which I was mentioning. I have them scanned now. I'll share those with you. Second is the quantum condition. Quantum condition is the same, what you have studied. Quantum condition is that all the possible, all the electrons that are permitted to circulate are only when the angular momentum of electron is integral multiple of h by 2 pi. Angular momentum is integral multiple of h by 2 pi. So L is equal to nh by 2 pi, that is mvr. This is the Bohr's quantization condition also I've told you. And quantum condition you can simply say where n is 1, 2, 3 and so on. Then, so first was nuclear concept. Second was quantum condition. Now, third one is stationary orbits. Stationary orbits. So while revolving in the permissible orbits, it was observed that electrons do not radiate energy. Electrons do not radiate energy. So the non-radiating orbits are known as the stationary orbits. Non-radiating orbits. These are known as what? These are known as stationary orbits. So basically, it's like whenever electrons are evolving in their suitable orbits, electron, if they do not radiate energy, then they'll keep on moving in the same orbit, and then the orbit will not appear to move. That's why we call it as stationary orbit. Stationary orbit or non-radiating orbits, you can say. Last one is frequency condition. Now see, electrons have a tendency of jumping from any orbit to any orbit, from first to second, third to fourth, any orbit. This we'll see also. Certain series are there. Those we'll see in today's class only. We'll see. Now, frequency condition is what? Frequency condition is E is equal to h nu. But this is the total energy always. So if two types of energies are present, one at higher level, one at lower level, so frequency multiplied by Planck's constant, that is this total energy, this will be equal to this h into nu. This will be equal to final energy minus initial energy. This is known as the frequency condition. Fine. As an electron, whenever you have an atom is there, an atom can emit or absorb radiation. Various orbits are there. Like this, you have orbits in complete circle form. So electron can jump also from a lower to higher orbit, or an electron can fall also from a higher to lower orbit. So this condition, this is known as frequency condition. Fine class. So these are the four postulates. First is a nuclear concept, that nucleus is present. Second is quantum condition. Third is that stationary orbits are present, which are non-radiating. And final is the frequency condition. This is known as the Bohr's famous frequency condition. So first topic which we did was Bohr's quantization condition, which said that L is equal to mvr is equal to nh by 2 pi, which is this equation. Now tell me class, till here, the quantization condition, Bohr's postulates, is it clear till here?
Yes, teacher.
All right then. Note it down. Any queries you have, let me know. This you have to write it from here. C class, after this, you have the concept of energy because this will be related. See, Atif was mentioning, remember centripetal force. So from there you can relate. For energy, Bohr's theory of hydrogen atom, you have Bohr's theory of hydrogen atom. So radius and velocity, few things are there. Let us calculate that. So C class, nucleus is present. Nucleus is present. Electronic charge will be E. And what is the atomic number? Atomic number is denoted by Z in chemistry, no? Z is the atomic number. So multiplied by this gives you the total proton charge in the nucleus. And electron is already there. Let's say this radius is R. Fine. Electron's linear tangential velocity is V. Mass of the electron is M. Fine. All these things I have mentioned. Now centripetal force will be equal to the electrostatic force of attraction. And centripetal force is what? mv square by R. Coulomb's law. Electrostatic force is simple Coulomb's law. So this will be Zk, Ze, Kq1, Q2 by R square. No, electrostatic force, how do we write it? K, Q1, Q2 by R square. So K written, Q1 is this. Q2 is E divided by R square. Now from here you can see R gets cancelled. So mv square is equal to kze square by R. So from here R can be written as kze square by mv square. Fine, this is what R can be written. Now see, from the quantization equation mvr, which is equal to nh by 2 pi, from here see the value of R. R will be equal to nh by 2 pi mv. This is the value of R. Now equate both these equations. Let's say this is equation 1, this is equation 2. This is also one important equation. This is also an important equation. Let us equate both of these. See, when you will equate, you will get kze square by mv square. Here you will obtain nh by 2 pi mv. Mass gets cancelled. One velocity, other velocity gets cancelled. Final velocity's formula will become, this will be 2 pi kze square divided by nh. This is the formula for velocity. Now velocity is this, but let us also calculate the value of radius. Because C class, in this formula, in this second formula, only velocity is remaining. No, velocity is unknown. So let us keep the value of velocity from here. So R was equal to nh by, nh was there, nh by 2 pi mv, right? So 2 pi m will be there. Instead of v in the denominator, we'll write it as nh by, right now that we have derived 2 pi kze square. This is the value of velocity 1 by v. This is written as 1 by v. So R becomes n square h square by 4 pi square m k z e square. This is the formula of radius. This is the formula of radius. So one is the velocity of the electrons. Second is radius of orbit. Radii of the orbits. All right. One more thing, class. If you keep all these values, no, value of n, value of h, obviously n you cannot keep. Planck's constant, 4, pi, mass of electron, constant, 9 into 10 to the power 9. All these values, if you keep, you will just be left with n square and z that will be unknown and depending upon atom and number of orbit. For first orbit, n will be equal to 1. For second orbit, n will be equal to 2. Similarly, z is the atomic number. For hydrogen, it is 1. Like this, you can conclude. So what you will find is if you put all the values, you will get 0.53 into n square by z, this much amount of angstrom left for the radius of it. Fine. This is about the radius and velocity. One more thing, let's see, that is the energies, kinetic energies. Let's see, then we'll come to the spectral series, which I was mentioning, that is the most important topic. See class, for the energy of the electron, no, mv square was equal to kze square by r, right? mv square by mv square by r, when we equated the centripetal force, when we equated it to the electrostatic force, this was what we obtained. We had started our derivation from here only. When we cancelled, see, mv square is remaining. Multiply half here, multiply half here. Half mv square, what are you obtaining? Kinetic energy. This is half mv square, which is equal to kze square by 2r. This is the formula of kinetic energy, kze square by 2r. Now there's a relation between kinetic energy and potential energy. Potential energy is basically negative of and twice of kinetic energy. So potential energy will simply be minus 2 kze square by 2r. So 2 gets cancelled. Potential energy is kze square by r. This is potential energy. Now, total energy is sum of potential energy and kinetic energy, which you call as mechanical energy as well. So, total energy will be sum of both of it, kinetic energy and potential energy. So, total energy will be minus kze square by 2r. These formula, no, these big formulas, questions usually do not come from this, as in numerical terms do not come from this. All right, you get these values directly to prove, show the derivation for the radius of the orbit, velocity. So these are much more inclined towards derivation part rather than the numerical part. Fine, so this is for it. Now after this we'll start something important, that is spectral series. Note these down, then we'll do the spectral series. Class, look here. Try to understand spectral series of hydrogen atom. See, energy, the formula of total energy that you've obtained. Again, if you put all the formulas, all the values that are present, so energy will be minus 13.6 Z square by N square. Fine. Now, for hydrogen atom, value of Z is 1. Atomic number is the first one only is the for atomic number for hydrogen. So E is minus 13.6 electron volt by N square. And class, remember, this is for electron volt. The SI unit here is electron volt, not joules. For joules, you have to convert this by multiplying it by 1.6 into 10 to the power minus 19. So this is the total energy of it. Now, Rydberg's formula is a formula. This is no derivation is there for Rydberg's formula. You just have to remember and learn this as it is. See, Rydberg's formula, 1 by wavelength. This is actually equal to a constant which is known as Rydberg's constant, multiplied by 1 by N1 square minus 1 by N2 square. Now, what is this N1? What is this the N2? I am telling you. First, just understand the formula. R is, that is Rydberg's constant, is simply 1.0973 into 10 to the power 7 per meter. This is Rydberg's constant's value. So by this, you can calculate any wavelength. The questions on Rydberg's formula are so many questions. So many questions are available for Rydberg's formula. Now, C class. What happens is, what is this N1 and what is this N2? See, I have told you electrons keep on jumping from one orbit to second orbit to third orbit, third to fourth, fourth to third. They can jump from a lower level to a higher level, as well as electrons can jump from a higher level to lower level, both lower to higher and higher to lower. Both of it is valid for an electron. And when the electron jumps from lower level energy level to a higher energy level and vice versa, it emits radiation that lies in the wavelength, that has a specific wavelength and frequency, and lies in the certain electromagnetic spectrum. Now, look at this. These are the various orbits that I've drawn. First orbit, second orbit, then third orbit, fourth orbit, fifth orbit, and finally the sixth orbit outermost. Now see, from anywhere in space, if electron comes from anywhere, any orbit you can take, 5th, 6th, 8th, 900th to 20th, any random one. But it comes finally back to the first orbit, from third to first, fifth to first, 18th to first, any orbit, but it comes to first. You call that series as Lyman series. The name is Lyman series. Got it, class? Then again, if electrons from any of the orbits come back to second orbit, this is the second orbit. So if it comes back to second orbit, so for second orbit, you can see this is known as Balmer series. This name is known as Balmer series. And if from anywhere the electrons come back to the third orbit, look here. So this series of spectral lines of hydrogen atom, this is known as Paschen series. If electron comes to the fourth orbit, this is the fourth orbit. See here, this is the fourth orbit. Then the spectral lines are said to be bracket series. And if it comes from anywhere but comes back to the fifth orbit, you call it as Fund series. P is silent, P Fund you write it, but you pronounce it as Fund series. So these are various series. Now see, let's see Lyman in detail. Lyman series, when N2 in the formula, the formula that we had seen, Rydberg's formula, N2 was there, N1 was there. So N2, that is the final orbit. The final orbit from where the higher orbit, you can say. Higher orbit can be any orbit. It can be 2, it can be 3, it can be 4, 5, any number. But first N1 is fixed. and one is fixed. That is 1 for Lyman series. Because this is the electron is coming from ground, from second to third to fourth or fifth, sixth, any of these back to the first state. And whenever the electrons, you say orbit is 1, n is equal to 1, we can also call it as ground state. This is also known as ground state. In the question, it can be referred to you as ground state also. Calculate the energy of hydrogen atom for ground state. So you will have to keep n as 1. After this, so what is fixed here? 1. You have to see from wherever electron is coming, it should come back to 1. Now, second one was Balmer series. So N2 will be 3, 4, 5, any value, but final one, 2 is fixed. Oh yes, one more thing, class. See, when this Lyman series, the wavelength frequency, it matches the electromagnetic spectrum's ultraviolet radiation. So UV radiation of electromagnetic spectrum is achieved for the Lyman series. Whereas for Balmer series, it lies in the visible region. Just remember for Lyman and Balmer, because for other three, no, everything is having infrared radiation. So that will become easier to learn. For Lyman series, for Balmer series, remember the spectrum also, region of electromagnetic spectrum. So UV region is for Lyman series. For Balmer series, you have visible region. N2 is fixed. Now, after ground state, after this ground state, just let me see, I have written it. Okay, this is written here. See, n is equal to 1. That is known as the ground state. After n is equal to 1, that is n is equal to 2. This begins the first excited state. After first excited state, n is equal to 3. It will become now the second excited state. 4, third excited state. 5th, fourth excited state. 6th, fifth excited state, like this. Because the first one is the ground state. That's why. So here also, no, that I was referring. This one, class, first excited state. It means in Balmer series, electron jump from any higher level back to the second orbit, or you can say to the first excited state. Both are valid for us. Then was the Bastian series. So for Bastian series, n can be any value, n2, but n1 is fixed, that is third. You can also call it as second excited state, and this lies in infrared region. For bracket series, same thing. N2 can be anything, and 1 is fixed, that is 4, and this also lies in infrared region. And last one is fun. Any electron jumps from any of the orbit back to fifth one, and this also lies in infrared region. First, tell me, is this part clear to all of you?
Yes, ma'am.
Clear? Atif, you tell me, if an electron jumps from 8th to 3rd orbit, which series will it be? Yes, Atif Ahmed. From 8th orbit to 3rd orbit.
Bastian series.
Bastian series. Yes, definitely, because this is coming back to the 3rd one. Next, Fatima, if an electron comes from 6th orbit to the ground state, which series will it be?
Lyman series.
Lyman series, perfect. Because ground state means n is equal to 1. Good. Hamza, if electron jumps from, let's say, 20th orbit to the 4th orbit, which series will it be? Hamza, from 20th orbit to the 4th orbit. Yes, Hamza. Unmute yourself, Hamza. Okay, you have answered no, Hamza. Hiba? What's your answer? From 20th to the 4th orbit. Yes, Hiba. Hiba, you there in the class? Yes, Fatima.
Bracket series.
Bracket series. Good. Hiba, did you understand now? Hamza. See, Hamza, Hiba. Here, last one you have to check. N is 4. It is coming from any orbit, be it 20th, whatever value I say. Last one is 4 and fourth one is the bracket series. I have kept it in front of you only. Yes, next, Krishna. From third excited state to first excited state. Which series? Third excited state to first excited state. Krishna.
Balmer series.
Balmer series. Good. Because third excited state means the higher one, that is fourth. And first excited state means second orbit. Because one was the ground state. So correct. It is Balmer series because this is the first excited state. This is ground state. This is the first excited state. All right. Yes, Sarah. Sarah, you tell me if it comes from the sixth orbit to the fifth orbit, if electron jumps from sixth to fifth orbit, which series will it be? Sixth to fifth, Sarah. Yes, Sarah, correct. It will be Fund series because it is coming from, though it is coming from this immediate orbit only, but you have to check the final one. From wherever it should come in the final one. Yes, Sarah Parkar, if it comes from first excited state to ground state, if electron jumps from first excited state to ground state, which series will it be? Yes, Sarah.
Lyman series.
Lyman series, good. Because first excited state means this one and ground state means first. Why I have discussed this in so much detail and I've asked all of you because this part is the most important part. Once you have understood this, no, once you have identified, now all your questions are easier. Using the Rydberg's formula, now you can even put the values in Rydberg's formula. See, for Lyman series, you know n will always be 1. For Balmer series, n1 will always be 2. Like these n1 values for the spectral series, you already know. Now you just require n2 from the question. Now clear to all of you? Yes or no? I hope it's clear now because all of you were able to answer. Any doubts you have, class? This part is important. Note it down. If you have any queries in between, you can ask. Just text me done once you write till here. Then I'll stop. If you have any queries, also any doubts from this part, let me know. Numerical solving, we'll do it in the next class then. Yes, Fatima, bracket series will also be in infrared region. Last three infrared region, all these three. Okay, if you all have done, then you all can leave. Those who have completed, you all can leave. We'll now continue on Tuesday now. All right. Okay, thank you so much, class.
Thank you, ma'am.
Thank you.